Yes, today I wanted to talk to you called. Oops. All right. So here we have two different scales. On the left, we have what we call an electronic balance, and on the right, we've got what we would call an analytical balance. What I'm going to do is I'm going to take a marker, a Sharpie, and I'm going to weigh it on the electronic and the analytical balance. Now, I actually did this, but I'm just kind of showing you via PowerPoint. If you weigh it on the electronic balance, it reads about 9.16 grams. If you take that same marker then and move it over to the analytical balance, you're going to get a reading of 9.1563 grams. Now, both of these readings come from the same marker, but the problem is that they're different numbers. So the question becomes, why are the numbers different? If it's 9.691, shouldn't it be the and the answer has to do with something called significant figures. So this is something we'll see happen in a lab. You take a marker and you weigh it on one scale versus another scale, you'll get different results. Now in this case, two scales that are different in terms of how accurate they measure stuff. So they are a different degree of certainty. If we take electronic balance, for example, this scale is certain only about the first three digits of the measurement. So it knows that the 9 is certain, and it knows that the 1 is certain, and it knows that the 6 is certain. Um, the analytical balance on the other, so we would say that this measurement, sorry, I'm getting carried away. We would say that this has three significant figures. If we're looking at the other measurement, this scale is certain about the first five digits. So it's saying it's actually a rounded number. And right, because if you take a 6 and you round it up, or now numbers, those figures are significant. So that's where the phrase significant figure comes from, is it talks about the number of numbers you have, and the number of numbers that are significant in a problem. So an one $1,600 or about 1,600, and an electronic balance only $300. So these scales are both very, very accurate because they're both expensive scales. More accurate things we can say. So here's what I want you guys to get from all of this, from this example of something that you can actually do in the real world if you take two different scales. The mass are going to round that mass differently depending on how accurate they are. Example, after five numbers or five significant figures. But the electronic balance, three numbers, just because it couldn't take that fourth and fifth number. It wasn't specific enough, right? It means though that yeah. So here we've got decimal places or five numbers, and we've got it over here rounded to two decimal places. Something that means though, this is important, right? The value three, those are both measured values, right? So the actual mass of the Sharpie probably has like a bunch of other numbers, the three here. Because we will never know what those numbers are unless we get a more specific scale. And then even then, there's still a bunch of other places worth of numbers that we could actually figure out, right? It's not like a Sharpie has a set mass because after you've measured the mass of the Sharpie, right, like you could measure it down to the atoms or down to like the electrons or down to the protons. Like you can get really, really specific about the mass of a Sharpie if you wanted to. So this is where significant figures come into play. Is at a certain point, we don't really care what the masses of a Sharpie is anymore, right? For some purposes, like if we're using it in an experiment, we might only need to know that it's 9.16 grams. Rarely will we need to know more than that about the measurement of a Sharpie. But if you're doing a lab with very, very specific data, you might need a couple extra decimal points if you're doing a chemical reaction, for example, in like a big fancy lab. Um, it could be a rounded number. So it's not really, it's actually, and it got rounded up. So something interesting to keep in mind here. Okay. When it comes to significant figures, there's really two rules you need to know. Rule number one is that every number that has a number between 1 and 9 is always significant. So when we're talking about numbers here, we're talking about digits. So like the ones place, the tens place, that sort of thing. The second rule actually has more parts to it, and that second rule is that zeros are sometimes significant. It's not always, it's not never, sometimes. Let me give you some examples. Here are three points: 0, 2, 2. So 100 million is that number. 3. What I'll tell you off the bat is that all three of these numbers have 3 significant figures. Number 9. So the 1 here could be 1, 2, 3, 4, 5, 6, 7, 8, or 9, and it would have still been significant. And same for the 2 and the 3. So there are 3 different types of zeros we'll see in problems. Let's talk about the first one that right here. Zeros are not considered significant because we leave them out of the count. Notice this is in blue. We significant figures and not significant figures both have 3 significant figures as well. So I'm going to refer to them as placeholder zeros. These are zeros that in the small number, like a number that's a decimal, those come in front of the actual numbers. The actual number 3 million. And the job of those zeros there is really just to say, this is a really, really big number. It's in the millions, right? Or small, this is a really, really small number, right? It's in the, I think, at the 10,000ths place. So these red numbers, significant figures. The blue numbers, I'm going to call those the in-between zeros. So these are zeros that are in between 2 non-zero numbers. Those numbers are considered significant figures. Okay, are just to say how big the 1, the 2, and the 3 are. So as scientists, we would say the 1, the 2, and the 3 are measured. If we wanted to make any one of these zeros significant, we would have to do some stuff that we'll get into a little bit later. 3, we're saying that we know we have exactly 103 pounds of something, for example. Now, we don't necessarily know 0.5, but we do know that right, we 3, if that makes sense. Okay, so placeholder zeros are important, in between zeros are important, and then there's a third type of zeros. And these zeros, this is kind of the most confusing part These are zeros that come after a decimal point, but also they have to come after a non-zero number. So you'll see a couple of examples here. 0.00, zeros that after this $1,200.00, for example, where you know it's exactly $1,200. Say it's 1,200, and then there might be some cents in there. We don't necessarily know. For example, um, has two sig figs, but 100.00 sig figs. Know that. Between zeros. And then for the our place zeros, they come after the decimal point, but they also come before these numbers 1 and 2, so those are still placeholders. Two sig, it comes after the decimal and after zero. Significant of sig here. So hopefully that makes sense. A placeholder zero just kind of makes a number big or really, really small. An in between zero comes in between a number and another significant figure. So here, in between, now it's longer a zero in between two numbers because it could be a zero in between a number and a zero after numbers that are significant, which makes it a little bit more confusing. I understand. Zeros are tough, but once you get used to them, you'll feel better. Between a decimal and then there has to be a number, and then you can have a zero. So yeah, hopefully that helps. Something that's good to know is that if you're in scientific notation, every digit you got there is significant. That's kind of cool. This is an always statement, not a sometimes, but an always statement. Right out in your scientific notation, zeros are all significant, so you can't get rid of them. 100 as 123 million, you would write it as 1.23 times 10 to the 8th. Over here, when you have zeros in front, small fourth times 10 to the whatever are your significant figures. And then, yeah, so that's pretty much just gets rid of your placeholder zeros, which are your only zeros that are not significant. And it has zeros. If you have 1.3 times 10 to the second, which would be 130. Totally different number, right? So that would really mess it up. You can't have that. It has to be the same number in both cases. Yeah, so here are some review problems. And we'll get a chance to kind of work over these together. These two are significant. So this first example would have second example, we also have this our placeholder zeros. This problem 3, but the second zero is not because it's not it's a placeholder zero after decimal zero. the whatever. So that would be 3 sig figs. Hopefully you feel more comfortable about sig figs. I probably won't right there. I probably won't throw a problem like that at you. So this helps me to go around in I guess very much. Take care.